Hello, we will look at PI control loops today. PI stands for proportional integral. It's part of the very well-known PID control loop, although the derivative, which is the D part of the PID, is outside of the scope of this presentation. So we're looking at PI through the lens of Structureware, which is a building automation solution by Schneider Electric. So in Structureware, as you all know, we write in script, and this is how we can utilize a proportional integral algorithm written in code as a function in a actual program that controls a valve or a subsystem of a HVAC piece of equipment. So here is the code for the valve command program. So if we go through it line by line, we've got a system enabled boolean. Is basically your fan proof. You get that from a different program that controls transitioning between system modes of operation and system states. So currently, if your fan's running, then the system enabled state is true. So we've got a supplier temperature, a set point, a conditioning state. So see how here where our variables are, our conditioning state is heating right now, but this is gonna be heating, cooling, idle, dehumidification. The unit state, it's currently in winter mode, but this is another state that the unit can be in, and it could be off. So the unit is completely off. We could be in summer mode or in winter mode. And we're gonna have a last integral, last error, which are variables that will allow us to pass and return values to and from the function. Here they are. And then we will have an execution rate, which will allow us to throttle how fast this program cycles through lines 1 through 42. And then that, it's nothing. So then we'll have our output, which would typically go to an analog output on a controller. Then a loop message, which is something that we get, it's a value that we get from our PI loop that tells us how our PID is running. And then finally a reference in Structureware to the function itself, so that we can reference it and call it into memory and into execution from this program. So if we turn around and we take a look at the variables in Structureware side by side with the variables in the program, you'll see that they match exactly the same, name by name. And what that allows us to do is that, as you well know, these are all binding variables. So these are variables that were created as points in Structureware or in the Andover continuum, Andover controller. And so there's gonna be a bindings page here where we can, as we've seen before, drag and drop, boom, and all our binding variables are bound in Structureware. So what's going on here is important because as you create these variables are not variables in the algebraic sense of the word. They're program or computer science variables. The difference is that these variables are addresses or locations in memory that have a specified size in bits, which is defined by the data type that you decide that these variables are going to be, defined by the keyword numeric or string or datetime or function. Then there's also going to be an input or output modifier, which is going to let the program know that this memory reference is coming from structureware rather than a memory location created in the program, local to this program. If we see this variable, however, this variable does not have an input or an output modifier and is not a function. Hence, this is a memory allocated in the local scope of the program, meaning once the program ceases to run, the value stored in last integral will cease to exist. However, any of the values stored in the memory locations defined by for example line 6, due to the fact that it has the input modifier, the memory is being allocated in structureware, not in the program. Hence, when the program ceases to run, the data inside this variable location will continue to persist, and when the program runs again, it will be able to fetch the value stored in this variable because the memory location referenced by the variable is in the scope of structureware rather than the program. So why is this important? Because you will see that there is the same relationship between a program and a function as far as creation of variables as there is between the program and structureware. You can think of structureware as the parent of the program and the program as the parent of the function instance that it calls, and we will talk about what that means in a second. So first, now that we know and we refreshed a little bit about how memories are, how variables are created, what they are, what the difference is between a variable in algebra versus the variable in computers, which is the storage or the reference to computer memory in a program. Or in a database, for example, like structureware, it's a program, it's the interface to a database in my mind. So anyway, the next thing that happens is we're gonna run a subroutine that contains our control logic, and then we will jump from that subroutine to the exec cycle control, which is execution cycle control, and then we'll use the program system variable, time in seconds, and then our execution rate variable or value stored in this variable to throttle how fast we're gonna jump back into control logic and execute what's in here. So by changing the value of exec rate, we can throttle the program and speed it or slow it down. So the first thing we need to find out is if the system's enabled. Once we know that the system is enabled, then we'll continue on with the program logic. If the system is not enabled, then we can just cease, and if the calculated integral is more than 0, then we know we have not been in this state yet. So we will run this function, and we will see why in a second, and then we will assign the next time that we go through this, because we run this function in the way that it is with the arguments that it has, the integral will be 0 next time. if we are still disabled, right? So then our hot water valve will just be assigned 100, and we'll see why that is in a second. And so perhaps before we get into all this logic of how we're using the PI function, now it's a good time to go ahead and look at the code for the PI function itself. So as you see, even though the PI function certainly looks very much like a program because it contains code and you're using the same exact syntax for all your logic, the syntax for declaring so-called variables is different, and the fact for that is because in reality these are not variables, they are arguments of this function. And so these arguments are indexed in a certain order, 1 through 10, and this order has to line up exactly with the arguments, with the parameters that you pass the instance of this function when it runs and it's called from this program, hot water valve command. So the first argument should be a sensor, second one should be a set point, the third and fourth should be just constant numeric values for your proportional gain and your integral gain. Fifth would be a direction of action, 1 for direct acting, 0 for reversed acting. Sixth is your error that you will need to persist between different instances of this function when it runs in a program. So what do I mean by instance? It's a word I've brought up a couple of times. So the thing about this code here is that it's not running until it's referenced in a program and then called into execution inside that program, as it is done, as we're doing here, basically in this line. So since this code is not running, is what in object-oriented programming would be called a class definition. Here the terms function and programs don't necessarily jive with the actual terms in computer programming, but just think of this as a recipe for how to make a cookie. And here in this program, think of this program as your grandma, and your grandma goes into her memory and starts remembering how to make a cookie. This is that memory reference in your grandma's brain, and then now she remembers how to make a cookie, and she makes a cookie, and this is an instance of the first cookie that she made. And then this is possibly the process of making the cookie, and then the value that we passed the first time that we run this code and we instantiate the memory reference of how to make that cookie in your grandma's brain, we go ahead and pass that value of the output of that instantiating to this water valve, and that would be the end result or the cookie, right? So the program finishes its execution on line 44, it goes back to the top, comes right back to line 21, and now on the second iteration of this program, grandma has to remember again and reference the how to make the cookie again, and now it creates another instance of making that cookie and then passes that value out, and when the cookie comes out the oven, boom, it goes right back into storage right here into this variable. So that is why I say this is an instance of the function, because the function itself doesn't do anything until it's instantiated into an object that will run at runtime, no pun intended, and output a value. So back to the code here. Let's finish looking at what this PI function is doing. So if the loop is enabled, so the loop enabled this argument number 8, which we can reference right here. This is the third one from the bottom, or the third one from the last. There you have it. So as you can see, temp, that's your sensor. Active supply, temp set point, there's your set point. So it matches argument per argument. So if the loop is enabled, that means we run and we calculate our variable. So if the loop is enabled, then we have to encounter a different decision. If our output value is 100 or 0, or the loop is paused, then this is what we'll do. We'll take the difference between the sensor and the set point. In fact, let's do something. Let's just do the else's because they're actually easier. So if the loop is not enabled, come down here, we'll see this is the else statement that matches the first if statement on line 16, and then we'll see that what we're doing is our integral value gets a 0, our output value gets 100. If this was direct acting, this would be 0, but because it's reversed acting and it's a normally closed valve, we want to start the loop with the valve closed. And then this is our message telling us that we're currently stopped. That's if the loop's not enabled. If the loop is enabled, if we're not already at 100% output or 0, and the loop is not paused, meaning that the program is not passing this value as a 0, then we will run the PI loop and we will do some PI controlling. So let's analyze this right here. We created a local variable inside this function. In fact, let's talk about that for a second. See how we're creating these variables here? Well, this function, when it becomes an instance in line 21 or in line 24, this function will at this point have to store some values, and it will have to manipulate some values. The problem is, once this function ceases to run and we move on to line 25, any values that were stored in variables local to this function, meaning variables that were created in this function, all those will cease to exist because nothing persists inside this function once it stops running. Just like in the example before, nothing will persist in this program if it ceases to run. That's why certain things have to be bound to data that is being stored in variables in StructureWare. So when we create these variables, we know that anything that we store in them, if we want to reuse it, if we want it to persist beyond the half a second that this function lasts into existence when called from this program, we must pass and take these values from outside the function, meaning from the program. That is why we have to have these arguments called stored error and stored integral, because by the time we're done, no matter any of the conditional statements, no matter what decisions we made about loop enabled or not, we will pass any value stored in actual error to stored error, and any value stored in integral value to stored integral, because these are the values that will go right back, because they're referencing memory locations outside the function, either in the program or in structureware. So they will persist, and they will be the same next time we call the function into memory from here. Okay, so now I think we can go ahead and look at the remainder of this logic. So in structureware, Boolean true and false is exactly equivalent to 0 and 1 numeric. So anywhere you have a 1, the program could interpret that as a true, and anywhere you have a 0, a false, and vice versa. So what's taking place here is that because we're doing direct acting or reversed acting, we're gonna have to either subtract the set point from the sensor or the sensor from the set point. So since any number multiplied by 1 has to be, it'll equal that same number, or multiplied by 0 it'll equal 0. If we multiply a Boolean expression times a value, if this examines to true, then it'll be interpreted as a 1, and then sensor minus set point multiplied by 1 equals sensor minus set point. However, if direction of action equals 0, then this is examined in a Boolean way as a false, which will be interpreted as 0, and then sensor minus set point times 0 would equal 0. And since this is the same but the opposite, then one of these two, every time this line of code is evaluated, one of these two on each side of the plus sign is going to be 0, and the other one is going to have a value. So value plus 0 equals value, basically, and that's your error with the direction of action applied. So once we have that, we'll multiply our constant proportional, and then we will get the integral value, which in this case actually should be the stored integral, because that's the value that we're getting from the computer. And then we clamp that. Once we add those two terms, we want to go ahead and clamp that value between 100 and 0, and that's why we nest the output of the minimum function inside the maximum function, and the output of that goes to output value. At this point, then we go ahead and calculate the partial sum, and then we times the partial sum of the error by the delta time. Scan is a system variable that of the program that calls the function, and essentially is how long it takes to run a cycle through the program, through all the lines of the program once. So once we have the delta t times the partial sum of the error, we assign that value, we store that value in the integral value that we've created, and then we print that we're running. We print a message. At this point, we would exit this end if, and we would come over to this line, and we would pass the actual error which we've calculated during this iteration of the function into stored error, and then the integral value that we got here, we'll go ahead and pass it back into the stored integral. Now, since this is a reference to to a memory location outside the function is actually an output of the function, much like the output value that we return through this return statement. This is perhaps confusing because we've been taught that everything inside the parenthesis is an input, but truly it's only an input to the function if it's a value, if it's passed by value, such as this guy's, right? If it's passed as a reference to a memory location, it could be an input, but it could certainly also be an output, because during the time that you allow this function to run, you can store any value you like in this reference to that memory location, and then reference that again from here or from here. So last thing I'll go over really quickly is the loop pause. The way it works right now, because you don't want to, this is essentially in fact a way to control anti-wind up integral reset. And so what happens is your integral, as you can see, will continue to add and add and add, and store that accumulated value into the stored integral. And if you allow it to continue to run, once your output is already at 100 or 0, then you run the risk of that accumulated value running so large that once it's time to throttle back, and in order not to overshoot, well, the integral calculated value will be so far out of reach, and it'll be nearly impossible to get back in time, and essentially it'll look like the loop output pegged at 0 to 100 and you lost control. So in order to avoid that, we want to pause the integrating of this control algorithm while we've already hit the max or min of the output signal value. Another thing, which is actually the experimental part of this, is that once you've in fact, so this loop pause, if it's set to 0, it's an argument that you pass the function. If it's set to 0, you can cause the same effect as though you had reached your min or max, but artificially as an argument. And this is just sort of a add-on for you to add more logic. So this is the portion that you can feel free to play with and see what you can accomplish with it. And essentially is exactly the same code as you'd have above, except that instead of multiplying the delta t into the partial sum of the error and then adding that to the integral value, we're just passing the integral value right through. We're not adding to it or subtracting from it. And that is what we're doing. In this logic is fairly simple to understand. If our system's enabled, we run and we control the valve. If it's not, then if our integral is higher than 0, as we've seen, it means we've been running the loop, and we need to now run the loop with a disable. And what happens if we disable? Well, we zero everything out, or we go to our output default state. So we zero out the integral value and we go out into default output value, which could be 100 or 0 or something else. Truly, it could be anything you'd like it to be. Feel free to change this to be your default value at startup of your loop. So anyways, because our last integral value is more than 0, we know this loop's been running, so we run the function one last time to zero everything out, and then once we run through this program once more, if integral is 0 and we're still in disable mode, then we just pass the default value we know to the valve, and we don't have to run the function anymore. So if the system's enabled but the conditioning state is in idle, meaning we're in the deadband, we're not heating or cooling, and we're in winter mode, we will run the function in pause mode. Else, there's a number of things that we could have. We could have that condition state in something other than idle, the unit state in something other than winter, but truly the only thing we worry about after that is if we're in heating mode and winter mode. And when we have those two conditions in series, then we actually run this loop as we should with no pause and enabled. If we are not heating or in winter, then we don't care, and we just do the same thing as though we were disabled. Now, why do we have all of this? It seems like some of it is redundant, but the truth is you could have a number of unknown states, and you just want to make sure that no matter what happens with the states that you are getting handed down from your state manager, you will always have this loop under control, and you can assert where your loop is going to be no matter what your state of operation is for the unit. Now, why do we have states? Well, the fact is, this is a hot water valve command program, and it doesn't have to know how to determine whether the whole piece of equipment, the whole AHU, is in winter mode, and it doesn't have to determine whether you're heating or cooling. None of that is something that pertains to the operation of a hot water valve. It's much more efficient to have that logic that defines the transitioning between different states of operation in a single central location that then passes those values out to all the other subsystem programs like the chilled water valve, outsider dampers, hot water, and so on. So this is that's what's going on here with your system enable and your different state variables. They're being passed to you by your state control manager. So and I believe that's pretty much all of it. So let's go ahead and run this now. Alright, so we will go ahead and enable the system. So our loop is running. And right now our temperature is 5 degrees above set point. Our loop started at about 20% and is quickly ramping up to try and catch up and close the valve. So I think possibly we can make we can make that faster if we go ahead and make this 80, and that should make our hot water, there we go, 100. So now let's come down to say 69. Muffin, let's go with 64.5. And 88. So it's starting to open. Now this is a normally closed valve because it's a hot water system, so 100% output is what you want in order to close the valve. So typically you want your hot water valves to fail in the open position, so that's why 100% is closed in this case. As you can see, pit loop works okay. It could possibly go a little faster. So now it's trying to catch up again. It certainly looks like it overshot by quite a bit. See how interestingly it does react as you would expect it to. Now we're just half a degree above set point, and it took for the valve to be 95.64% closed. And so the pit loop, once it hits set point on the spot, it actually does stop to integrate. Even though we don't really have anything here to tell it to pause, it pauses naturally or organically. So you see the pit loop is running, but it actually paused. Increase, then it goes up, it hits 100, and now it pauses. And it pauses so that we do not wind up our integral to a value so far out of reach that once we need to reset, it would take hours possibly for the integral to subtract the partial sum of the error down low enough to get it back in the range that it's needed to affect the output signal. See how we've been a while now at 100%. We've been paused for quite some time. If the integral would have continued to accumulate, it would take at least as long for the loop to get back in control. So let's see how long it takes for us to regain control and get unpegged from 100. It took nothing more than half a second. So that's proof that our integral stopped adding once we hit 100. Thank you for watching. That will conclude this presentation.